Let's say we have two poles, A and B. Einstein is standing right in the middle of these two poles with some supernatural ability to see both poles at the same time. Let's say lightning strikes both poles simultaneously. Since Einstein is standing in the middle of these two poles, the DTS equations for both will be the same, and thus he would see lightning hit both poles at the same time. But let's say Newton was sitting in a train that was traveling at half the speed of light. He was also traveling parallel to both of these poles. Once again, he has the same supernatural ability as Einstein. Lightning hits both poles simultaneously, but since light travels at a constant speed and the train is moving towards pole B, the distance needed for the light to travel to Newton's eyes from pole B is lesser than the distance needed for the light from pole A to reach his eyes. This means Newton would think that lightning struck pole B before it struck pole A. Both Einstein and Newton would think about reality differently, just because Newton was sitting in a train. This simple thought experiment was one of the many factors that propelled Einstein to change the field of physics forever, starting with his theory of special relativity. In the late 1800s, scientists still believed that light traveled through a medium called the ether. Like sound was a disturbance in matter, light, being a wave, should be a disturbance in some other medium, which they call the ether. There were two simple experiments conducted with some rather interesting results. The physio experiment was conducted to find out if the ether was dragged by another moving medium, such as water. It found out that there was a very slight change in the speed of light when it traveled through moving water, compared to still water. This raised the theory of partial drag of ether, but essentially gave evidence proving the ether theory. The Michelson-Morley experiment, on the other hand, aimed to find out the relative velocity between the Earth and the ether. It is regarded as the greatest failed experiment in history, because it instead showed that there was no change in the speed or direction of light, essentially proving that the ether did not exist. The theory on how these experiments worked is rather complex, so I will not explain them in this video. Einstein came along in 1905 and theorized something radical, aligning himself to Maxwell's theory of electromagnetism from the 1860s. He theorized that the ether did not exist, and that instead, light traveled as an electromagnetic wave, and the speed of light in vacuum was always constant. He thought about what would happen if light traveled at a constant speed, what would change, and he theorized three phenomena. But firstly, he defined a few things. There are two tenets to his theory of special relativity. The first being that the speed of light is always constant in vacuum, no matter the motion of its source. This basically means if you throw a ball in a car, from your perspective, it will travel at this velocity. However, in the perspective of someone standing still, it would travel at this velocity. If you used a flashlight, however, both you and the person standing still would see the light travel at c, or around 300 million meters per second, no matter how fast you were traveling. The laws of physics apply the same to all reference points or frames in the world. Let's prove this one. Let's say you take a ball, you throw it up, and you catch it. It follows all laws of physics properly. Now, start walking. While walking, throw the ball up and catch it. Once again, it feels normal. Even when you are moving, the laws of physics are still working on you the same as when you were standing still. The first theorized effect is the breaking of simultaneity, which I already discussed in the intro. This concept is kind of frightening because certainly we don't know the exact time any event occurs. This means that different frames of reference will view the world differently. This sets up the basis of relativity. All reference frames different views on events or objects, but this doesn't mean that only one of them is correct. In fact, all reference frames are correct. They're just relative to each other. The second effect is time dilation. Let's say Newton flashes a light at a mirror in his train car. He sees the light travel 1 meter ahead and 1 meter back. What about what Einstein sees? Well, he sees the light travel in a slanted motion. So from Einstein's reference frame, the light traveled a greater distance than to Newton's. This means the light traveled a larger distance at the same speed, which means that it must have been traveling for longer in Newton's car. This means from Einstein's perspective, time has slowed down for Newton. This is time dilation. This means the faster an object travels, the slower its time is relative to an object standing still. However, this causes a paradox because we can take both reference frames to be either stationary or in motion. If we consider the train to be stationary, that means the world and Einstein are moving. This means from Newton's reference frame, time has slowed down for Einstein. So how can both of them be right? Well, this causes a paradox. Now comes the time dilation formula. Back to the train. Let's take the distance that the light traveled from Newton's frame to be speed times time, ct, and the distance that the light travels from Einstein's frame to be ct prime. Now, the final side of this triangle will be vt prime, where v is the speed of the train. Now, we can use the Pythagoras theorem to find out that the t prime is equal to this. T prime is equal to t divided by the root of 1 minus v square by c square. This is where t is the duration of the event as observed by a reference frame co-moving with the event, whereas t prime is the duration of the event observed by a reference frame relatively stationary to the event. Now, usually this is taken as a variable gamma, or the boost factor, where gamma is always greater than 1, since the denominator will always be between 1 and 0. Notice that this also shows that v should be less than c, or else the denominator would be imaginary or undefined. It shows that nothing can travel at or faster than the speed of light. Also, we can rewrite the time dilation formula in terms of gamma, like so. The third and final effect is length contraction. Maths time. Stop the video right now if you don't want your head to hurt. Let's say Newton is standing at this end of the train. He shines a laser at a mirror at the other end of the train and measures the time it takes to reach his wall again. From Newton's reference frame, light will simply travel forward and backward at speed c. Let's say the distance it travels the round trip, which means both forward and backward, is ln, n for Newton, and the time it takes to travel is tn, n for Newton. This means the distance the light travels should be ln is equal to ctn. Now that we know that the time taken in Newton's reference point should be the time taken in Einstein's reference point divided by gamma, according to the time dilation equation that we found out just before, this means ln is equal to c times te by gamma, where te is the time that Einstein measures. Next, if Einstein measures the time the light takes to touch the mirror, it will be the distance he measures of the length of the apparatus, which is le by 2. Remember, le will be the round trip, which means forward and backward, plus the distance the apparatus travels in the time it takes the light to travel, given as v times t1, where v is the velocity of the train. When it travels backwards, it will be the distance of the apparatus, le by 2, minus the distance the light takes to travel, given as v times t2. Since these are both distance formulae, we can simply use the DTS equation to, well, find the time taken, which is time is equal to distance by speed, speed being c. Now we simplify, and since the total time that Einstein measures from his perspective would be t1 plus t2, we add these two together and get gamma squared times LE whole by c. Finally, we plug it into our previous relationship between ln and te, and this shows us that the distance that ln will be equal to is Le times gamma. Since gamma is always greater than 1, it shows that ln will always be greater than Le. This shows us that the distance, or any length that Newton measures, will always be greater than what Einstein measures. This effect once again works both ways. So Newton's train will be shorter from Einstein's perspective, but Einstein will be thinner from Newton's perspective. Finally, the age-old question: what would happen if you traveled at the speed of light? First of all, you can't travel at the speed of light. Gamma shows us that if v is equal to c, the answer becomes undefined. You can get as close to it as possible, but never really reach the exact speed of light. This is why Einstein famously said, "The speed of light is the only constant." Anyways, that's it for today's video. Bye, nerds.